Happy Friday, everybody. Let's take a look at the problems from yesterday. What you're doing essentially with the problems in this practice problem set is you are rewriting trigonometric equations into a different form using trigonometric identities. Very specifically, and you were going to get this in a handout here in a bit, but the top of this page is showing what I'm talking about here, that you can use trigonometric identities to solve equations by rewriting the trigonometric equation in a simpler fashion by employing trigonometric identities. I mean, a really simple, almost childlike example would be for you to be asked to solve this. Tangent of x equals cos squared of x plus sine squared of x. This may look like a very intimidating equation because it's got a smattering of three different types of trigonometric functions in it, but the fact of the matter is, since cos squared of x and sine squared of x added together always give you 1, you're asked to solve that equation. Right? It's not, I mean, that's to me, this is a very obvious situation. And then you would say, well, where is tangent of a rotation angle 1? You would say it's 1 wherever x and y on the unit circle are both equal to each other, which would be here and here. So it would be pi over 4 and what I believe is 5 pi over 4. Okay? That's what we're doing in this section. So let's start, please, with the textbook. Does anybody have any questions from the textbook? I'll give you a minute to look while I do something. Any questions from the textbook? So take a look over your work, please. All right, fire away.
1B.
Sorry?
1B.
1b. So we're asked to solve sine of 2x minus sine of x. This is a classic. It's not classic like Dark Side of the Moon is a classic album. I mean classic like you would see it on an exam. It's a very common question. Sine of 2x minus sine of x is equal to 0. Remember that ideally when you're solving an equation, and you know what? This is true whether it's trigonometric or any other type of equation. At this level, for the most part, algebraic equations are solved by rewriting the equation as a series of factors being equal to 0. And when I say a series of factors, what that means is each of them are multiplied by all of the other ones. So if you had A multiplied by B multiplied by C equals 0, then you create 3 different equations that you solve individually, right? So how do we go about expressing this as factors? Well, we're going to start off by going to our formula sheet and seeing that sine of 2x is equal to 2 sine x cos x. Minus the sine of x, and now what we've done is we've created a factor. It's a common factor. Because again, just to break this down as simply as I can, we have two terms. You have the yellow term minus the blue term. So what's common? What's a common factor? Well, 2 sine x has 3 factors. 2 sine x and cos x. 2 sine x cos x has 3 factors. 2 sine x and cos x. Sine x has 1 factor, sine x. So there's a sine x that's common. We can factor that sine x out. And when we remove the sine x from this by dividing this by sine x, you're left with 2 cosine x. Minus, when we divide this by sine x, we're left with 1. I mean, sometimes I would say, if we take the sine x out of this, what are we left with? And that's maybe not the best thing to say because some people will go, well, you're not left with anything. No, you're left with the number 1 because when you factor, you're dividing. And now we're at a stage where you can take each of these factors. Now we've got 2 factors multiplied giving us 0. And each of those factors is something that if we set equal to 0, we could solve. I can figure out where on the unit circle the rotation angle has a sine of 0, and then this becomes 2 cos x minus 1 equals 0, which you rearrange to cosine x equals 1/2. And I can very easily figure out where on the unit circle the cosine of the rotation angle is 1/2. So let me ask you this then, Ben. You're good from here? Okay. You'll notice again, I'm kind of forcing everybody to rely on the unit circle here. I'm not going to go through a reference angle approach on your calculator. You can do that if you like, but when you get sines or cosines equal to 0 or 1 or -1, you get problems associated with that method. I think it's best to just say sine is the y coordinate. So sine of x, sine of the rotation angle, is at these two locations. And then you can write out the angles. Other questions from the textbook? Go ahead. 3A. So, and by the way, I didn't really, this was from 0 to 360, so you're fine with using the domain there for that. Is that right? Okay. So now we're in radian mode. We want to go from and including 0 up to but not including 2 pi, and you said A. Okay. So we have cosine of 2x minus 3 sine x equals 2. Now, we're going to replace cosine of 2x with an equivalent expression, but when you go to your formula sheet, cosine of 2x has many different disguises. Cosine of 2x can be cos squared of x minus sine squared of x. It can be 2 cos squared x minus 1. It could be 1 minus 2 sine squared x. And what we have is, I'm going by memory here, we have cos of 2x minus 3 sine x equals 2. So if we were to take cos squared of x minus sine squared of x and put it in here, we would be setting ourselves up for more work, because then we would have an equation that has sines and cosines in it. In the end, what we want to do is use this as a replacement for cos of 2x. Well, not that, I suppose, just this part. Right? I think you got my drift, but we're going to replace cos of 2x with 2 cos squared x minus 1. Then at least we have a single equation that has, among other things, it has cosines, but it doesn't have sines, it doesn't have tangents, it doesn't have anything else.
I used the third one because I thought it was supposed to match.
Oh, geez. I'm sorry. We're going to use the third one. And I was just about to ask Evan what he felt the problem was, because Evan had that confused look, and it isn't that Evan's confused, it's that I am. We need to replace cos of 2x with an expression that contains sines, because down here we have a sine, so we want all sines, among other things, which will be the 2. I apologize. Okay, so I'm just going to finish it here. We're going to end up with 1 minus 2 sine squared of x minus 3 sine of x. So I'm putting this here, equals 2. Does that look okay? So now I see that it's quadratic. It's quadratic in sine of x because the sine of x is being squared. I have negative 2 sine squareds. I would much prefer to have a positive number of quadratic terms or quadratic pieces. So I'm going to move all of the terms to the right-hand side, where I'll be left with 0 on the left. I'll have positive 2 sine squared of x. I will have positive 3 sine of x. And I'm going to have 2 minus 1, which is plus 1 equals 0. Does that look okay? Okay. I was just, as I was writing that, I was just doing a b squared minus 4ac calculation to make sure it's factorable. If you do calculate b squared minus 4ac, I believe you get 1. 1 is a perfect square, so it's factorable. So how do we factor this? Not only are, it doesn't matter if you put 0 on either end, not only are the quadratic trigonometric expressions almost always factorable for an equation, they will be factorable with very few choices. Like, you're not going to have some wild big numbers. 2 sine squared x is going to be 2 sine x and sine x. Well, the one's got to be 1 and 1, right? Everything's positive, so if this is factorable, which it is because the discriminant is a perfect square, then that has to work out. And if you FOIL that out, do you see you get 3 sine x?
Yeah, I just did my factoring wrong.
Okay. So you think you're good from here? One final point. If I set this factor equal to 0, I end up with the statement sine of the rotation angle, sine of x is equal to negative 1/2. And when I set 1 equal to 0, I'm going to get sine of x is equal to negative 1. And again, I'm assuming, I really hate to just hand wave it away. I don't mean to be dismissive, but these two equations really are almost a 20-1 thing. Although in 20-1 we don't worry too much about all the quadrants. We do talk about them. Let's get back to this, and again, I apologize for my head being elsewhere. Other questions from the textbook? Go ahead, Evan. 10? This is a great question, and I've seen a question similar to this on a diploma exam, and it's why of all of the ones in your textbook, this is one I think we have to talk about. This looks really intimidating until you go back to what I told Ben, which is that when you have factors being multiplied by each other, if the product of all of the factors is 0, that means that each factor can be set equal to 0. So I'm going to rewrite this just to make my point. We have 7 sine x plus 2 multiplied by 3 cos x plus 3 multiplied by tan squared x minus 2, and this is equal to 0. And because there's a multiplication in between these three, each of these three factors, if any of the three factors is ever equal to 0, the whole right side will be equal to 0, which makes the equation true. So it's the basis for how we solve quadratic equations. And that means that we're looking at this equation now. We're looking at 7 sine x plus 2 equals 0. We're looking at this second equation, 3 cos x plus 3 equals 0. And we're looking at this equation, tan squared x minus 2 equals 0. The question says, how many solutions does it have? And I suppose we could solve this, but I'm going to tell you that I don't want us to solve it because I can change the question so you can't solve it. Okay? You'll see how that will work in a second. If we were to begin to solve this first equation, we would have sine of x is equal to negative 2 over 7. And negative 2 over 7 is a number between negative 1 and 0. I'm thinking that way because sine is the y coordinate on the unit circle. So if I were to look at the unit circle, remember on the unit circle the radius is 1. This is negative 1. So negative 2/7 is some number in here. And I can see that there will be 2 locations, which means from 0 to 360, I'm going to run into 2 solutions. And we get used to that. We get used to the idea that if you have sine of something equals a number or cosine equals a number, there's 2 solutions in the first revolution. So there's 2 there. 1, 2. That's not 11, it's just a tally. When we rearrange this, we get cosine of x equals negative 3 over 3, which is negative 1. And using our knowledge of the unit circle, there's only one place where that's going to happen, which is over here. So the reason why this does not have two solutions is there's not two different places on the unit circle that have an x-coordinate of -1. And I'm focusing on the x-coordinate because it's cosine, not because there's an x in the question. So we can add one more to our tally. Now, when you have this equation and you rearrange it for tan squared of x, you get tan squared of x equals 2. But that means that tangent of x can be equal to √2, or tangent of x can be equal to -√2. Because when you take the square root, you go plus or minus. In other words, this is linear, and it produces one solution. But because it's trigonometric, that one solution branches off into two. This is quadratic, so it produces two solutions. But each of these two now linear equations will produce two, because that's how trigonometry works. Like √2, I don't want to talk about reference angles here. √2 is about 1.41, roughly. So that means tangent of the rotation angle is about 1.4, which means the y-coordinate is about 1.5 times bigger than the x-coordinate. And that would be a position, say, about here, where if you took this y-coordinate over that x-coordinate, maybe here. But there's some point that's going to be in quadrant 1, and there will be an opposing point in quadrant 2, which will make it 2 solutions for tangent of x equals √2, but it will also give us two solutions for tangent of x equals -√2, and then we can add them all up and get 7. See, and the reason why I don't want us to solve this is I've seen questions like the following. No. I've seen questions like the following. And the question is, how many solutions does it have? And then they tell you before they ask you that some things about A, B, C, and D. They tell you, for example, that D is bigger than A, that C is less than B, and that F is greater than 1. And they say, how many solutions are there? Now, you can feel free to make up numbers, but it's going to be more confusing. If D is greater than, I meant to write A, if D is greater than A, then when you rearrange this for sine of the rotation angle, you're going to get D over A, but D is bigger than A, so D over A is a number bigger than 1, and guess what? There's no solutions there, because sine of an angle can't be bigger than 1. Nothing. Here, C is less than B. Well, that means if you rearrange this, setting it equal to 0, cos of x will be -c over b, but c is a smaller number than b, so it's like 1 over 3, -1 over 3. The bottom line is you're going to get a number here less than 1, which means you'll get two solutions. It will be two locations in quadrants 2 and 3, assuming it's saying from 0 to 2 pi. Right? If f is greater than 1, how many of you see that there's no solutions here? You're going to end up having sine squared of x is equal to f, and f is a number bigger than 1. So when you take the square root of it, you're going to have plus or minus root f, but root f itself will still be bigger than 1. You take the square root of any number bigger than 1, it will get smaller. But it's never going to be 1 or less than 1. And sine cannot be outside of the range from -1 to 1. So this would be kind of a trick question. There's only two solutions. Anyway, are you okay with that? Other questions from the text? Does anybody have any questions from the handout? JV? You're going to have to repeat that, please. 1B? On which page? Okay. Number 4B. D. Got it. Okay, sorry. I was just a little confused because you were saying 1. 26. 25. 4D. Okay. It looks like what we're going to have to do is apply the difference identity for tangent to tangent of pi minus x. Okay? So when we take a look at that difference identity for tangent, oh boy. It is tangent of a minus b equals tangent of a minus tangent of b over 1 plus tan a tan b. All right? So I have 2 tangent of x plus, now I'm going to use this bottom identity. Right, I don't care about the top one. I'm going to use the bottom identity where alpha is pi and beta is x. Okay, so this is going to be plus tangent of pi minus tangent of x over 1 plus tangent of pi tangent of x. This is going to be equal to root 3. And you know what? What honestly kind of frightened me a little bit is I haven't done this question before. This is a new set of practice problems, and you guys are kind of the guinea pigs for it, so to speak. The lab rats, no offense. Okay. But I can see it's going to clean up pretty nicely. Because tangent of pi is a number. It's not like tangent of x, which is variable. Tangent of x is a variable because it has x in it. Tangent of pi, when you think about it, remember, tangent of a rotation angle is the y-coordinate over the x-coordinate, and pi on the unit circle is right here. And the y-coordinate there is 0. This is negative 1, 0. So tangent of pi is 0 over negative 1. Tangent of pi is 0. So that means that, let's put 0 in for tangent of pi. You have tangent of x plus 0 minus tangent of x over 1 plus 0 times tangent of x. And this is equal to root 3. And I'm glad you asked about this question, because as much as I went on a few minutes ago about the unit circle and not talking about reference angles, tangent is maybe an exception to that rule. Okay? We have 2 tan x plus, now, what do we have on the bottom of this? On the bottom of this expression, for anybody watching at home, the bottom of that expression has a value of 1. So we don't need to write over 1. If I say, yesterday I ate 3 donuts, I don't have to say 3 over 1 donuts. I could just say I ate 3 donuts. The top, on the other hand, is equal to negative tan of x. because 0 minus tan of x is negative tan of x. And that means, look what happened here as soon as you applied that next step, that last step. You have 2 tan of x minus tan of x, which is 1 tan of x. So you have tan of x equals root 3. Do you see where I went with that, JV? I can tell you have a question. Go ahead.
So where did the denominator?
Well, this denominator is equal to 1. I mean, I could write over 1. But 0 multiplied by tangent of x is 0. So we're left with 1 plus 0, which means we're left with 1 because 1 plus 0 is 1. And I just don't need to write it. Good? Okay, so now we have 2 tan x minus tan x, which is tan x, equals root 3. Now, I know on the unit circle where the tangent is root 3. And let me show you where it is. We talked briefly about this one other time. It is up here at this point where x is 1/2 and y is root 3 over 2. And I hope you see when you divide y by x, the over 2 and the over 2 cancel. If you catch my drift, you're going to be left with root 3 over 1. Or another way to put it, the y coordinate at this point, and that is a horrible circle, but the y coordinate at that point is root 3 times greater than the x coordinate. So it's pi over 3. And then the other one, of course, would be down here where they both have the same values for the numbers, but they're opposite. They're both negative. You know, if you want to find a reference angle here, put your calculator in degrees and take the inverse tangent of it, and you'll get 60 degrees, which is pi over 3. And then you say, well, it's in quadrant 1 and 3 because tangent is positive. This is sometimes I say this and then I have to catch myself. This question, I was going to say, is something I don't think you'd see on a diploma exam. But the math diploma exam is, it's very unpredictable. Sometimes I see a question on there and I go, wow, that's a really high level question. It turns out, I want to reinforce this thing that we've talked about before. This is not a difficult question unless you just freeze. If you just look at it and expect something to pop into your head, it's probably not going to happen. But if you look at it and say, okay, I have a difference, I'm going to try, that's where the word try comes in, the difference identity. Then at least you get your foot in the door and you can start taking a look at different things that might help. Other questions? Liam? 4B? This is that one that I said I think is dirty. It's not dirty. I actually do believe, we're going to have to wait, I do believe that I don't think you would see this on a diploma exam. The problem with this is that it looks like kind of an identity, doesn't it? Like sine, cosine, and then all of a sudden it's cosine, cosine. But there is an identity there's lots of identities that are not on your formula sheet. There is an identity that we kind of learn about in earlier grades. And it leads us to the fact that something like sine of 20 degrees, well, go ahead and calculate these two. What is the sine of 20 degrees and what is the cos of 70 degrees? And I don't particularly care what they are. I care about the fact that you see they're equal. And they're equal because those two angles add up to 90 degrees. The reason for this is if I draw a triangle with a 20-degree angle here, and I say, what is the sine of 20 degrees? It's going to be this. I don't want to use A. It's going to be, well, it'll be the opposite over the hypotenuse, right? And if I say to you, what is the cosine of 70 degrees? Well, 70 degrees is up here because these two angles have to add up to 90. Well, that cosine of 70 is equal to the adjacent over the hypotenuse. But the adjacent to 70 degrees is the opposite to 20. And that's a useful thing here because if this was sine of theta cos of theta plus sine cos, then we could use an identity for sine. And this cosine of 78 degrees is equal to sine of 12 degrees. So this becomes sine of theta cos of 12 degrees plus, I'm going to take the liberty of writing this cos of 78 first. Of course, I'm writing it as sine of 12. Well, how does the identity appear on your formula sheet? I better look. For the identity for the sine of the sum, is it sine of A cos of B plus cos of A sine of B? Okay, then we'll leave it alone. This is cos of theta sine of 12 degrees. This is equal to root 3 over 2. Now there's one other thing that is new to you here that I wouldn't have thought to ask, but I could see this on a diploma exam. When we put these together, we get sine of theta plus 12 equals root 3 over 2. So, how do we solve this? This is for one revolution. What we say is that the y-coordinate of the rotation angle has to be equal to root 3 over 2. Well, we know where that is. We should anyway. It's at the 60-degree reference angles in quadrants in quadrants 1 and 2. It's at those two locations. That's where sine is equal to root 3 over 2. So we're allowed to work in degrees because it has this plus 12 degrees. This rotation angle would be 60 degrees. But that means that 60 degrees is theta plus 12, so we have to subtract 12 to get theta. 48. The other rotation angle is 120 degrees, but that 120 degrees is the rotation angle. And if this is equal to theta plus 12 degrees, and this is equal to theta plus 12 degrees, then you have to solve each of those for theta. And again, the more I think about the diploma exam, the Math 30 diploma exam is maybe one of the, in terms of math and science, it's the most challenging one. I mean, they have these guys and girls working in Edmonton on this stuff, coming up with weird questions for these exams. Anyway, I'm going to, let's say 10 to 10? 10 to, what time is it? I guess I can just look at my computer. 10 to 10, so we have about 45 minutes left. I'm going to pause there. I'm going to hand out some review materials for you because some of you may not have any more questions. And we're kind of getting into an area where, as much as I say, yeah, this could be on the diploma exam, we have to play this game smartly. We don't want to get confused by stuff that may be on the diploma exam. We want to try to focus on the basics before we get to this stuff. And I know some of you have already done that, but I don't want to confuse too many people with this stuff. I'm going to hand out some review materials and give you some direction in terms of what you should be doing to get ready for the exam on Tuesday. Then I can come back up here and I can go over some more problems if you like. Okay, and they can be any types of problems. You were expected to know the properties of the tangent function. So that's that graph that has all of those asymptotes, those vertical asymptotes. You're going to have to go back and look at lesson 5.3 from the previous unit to remind yourself of that. And you have to know the properties of the graph of tan of x so that you can find the properties of the graphs of transformations of tan of x. Then we actually started off this unit by saying, look, you can solve any trigonometric equation graphically. And you will be asked on your unit exam questions that test your understanding of that. Okay, so for example, I might tell you that you have this equation. And I might say to you, what are two different graphs that you could graph so that the points of intersection show the solutions? Well, you could just graph this as a function and look at x-intercepts, or if you wanted to, you could graph y equals tan of x, and you could graph y equals 3 minus cos of x, and look at the intersection points. Because if I take that equation and I move the cos of x and 3 over, I get tan squared of x. There should be a squared here. I get tan squared of x equals 3 minus cos of x. So left side equals right side. I would test that on my calculator. Anyway, I'm reminding you here that given the opportunity to find answers to an equation graphically, grab it. If it's multiple choice, nobody cares how you're getting the answer. Okay. Make sure, of course, when you're doing this in your graphing calculator that you use degrees so that you recognize the particular angles. And then the other thing that we looked at before we got into identities is transformations and applications of sine and cosine functions. So these are problems like the water in a harbor going up and down, or it could be the frequency of a police siren going up and down over time. And you're asked questions like, how long after midnight is the water 20 meters deep? Or what percentage of the time is the water less than 5 meters deep? And you solve these on your graphing calculator. But I want to highlight a couple of things here. Make sure that your window settings go vertically to an amplitude above and an amplitude below the vertical displacement. So the vertical displacement is d, the amplitude is whatever the absolute value of a is. So take the vertical displacement plus the amplitude, the vertical displacement minus the amplitude. Your vertical window settings, your y min and y max, have to be roughly in that region. Otherwise, you won't see it. You also have to graph one complete period horizontally. So you need to look at b, and remember that the period is 2 pi over b, and then you can figure out the period, and then you can go x min is 0, x max is whatever the period is. And finally, you have to use radians unless you see a degree symbol. And I have never, ever seen a degree symbol on an application problem. Okay. You also have to be able to come up with a formula for things like, well, you know the assignment that is due today, right? That I'll take in when I remember. You had data on that graph, right? Could you come up with an equation? Yes. So if I gave you a problem that said the maximum depth of water is 25 meters and it occurs at 1 o'clock, and the minimum depth is 8 meters and it occurs at 3 o'clock, you could figure out the equation relating that data. Or if I gave you a Ferris wheel question, you could determine the maximum height and the minimum height and the period and work backwards and determine the equation. Now the rest of this is all about identities, and we've talked about this enough times. I'm just going to go to all the identities first. Right? You have Look at this. But they're on your formula sheet. You got quotient identities. You got Pythagorean identities. You got reciprocal identities. You got a sum and difference identity for sine, a sum and difference identity for cosine, a sum and difference identity for tangent. Like, this can be overwhelming if you lack experience in working with this stuff. Because we also have a double angle identity for sine, 3 double angle identities for cosine, and 1 double angle identity for tangent. So if you are not familiar enough with these, you just cannot do the work in the time given. You can't. If you're going to look at a proof, let's just say, and then you have to go to the formula sheet and start picking an identity and seeing if that would work, and picking an identity and seeing if that would work, I am sorry, you're not going to finish the exam. You need to see stuff like sine over cosine is tangent. Or like, who said the other day, for tangent cosine, can't we just write sine? Was that you? Yes. I mean, if it were a written response, you'd want to show why that happens. But these are things you need to start seeing. And, you know, I'm not trying to scare you, but you're kind of running out of time, right? Hopefully you've gotten better and better and better at this. We still have a few days, but when working with trig identities, which I have here, or when proving trig identities, I just added one more thing to the bottom. You know, when you're proving an identity or you're working with identities in general, try changing everything from sine to cosine. Try factoring. Try bringing fractions together. Keep your eyes peeled for things that you've seen before. The most obvious illustration of that is you see sine squared plus cos squared. It's 1. If things get too ugly, too weird, too confusing, go back to the beginning and try something different. Because as we've seen, sometimes if you try replacing all ratios with sine and cosine, it might take you down a road that is really bumpy, whereas if you just factored first, it becomes very easy. And then the last thing I've got here is for proving an identity. Just make sure you keep your eye on the left and the right side. Working on the left side, keep your eye on the right. Know what you're trying to accomplish. And I just talked about using trig identities to solve equations. But one final thing, non-permissible values, remember you look in any denominator. So if you have a trigonometric ratio in an expression that is in the denominator, that cannot be equal to 0. If you have a trigonometric ratio in an expression that has a denominator in it, that denominator cannot be equal to 0. So as soon as you see tangent, cosine cannot be 0. Because tangent is something over cosine. As soon as you see cosecant, sine cannot be 0. So now I'm going to hand out the multiple choice and numerical response packages. There's 2 of them, and then you can get to work on that. And my advice would be to get as much done for Monday as you can, right?